So my name is Sarah Armitage, and my co-investigator, Ron Yang, and I are thrilled to be speaking with you all today and look forward to feedback on this project. So there are two motivations for this project. The first is that truck freight is a hard to decarbonize sector, yet one that is quite important for meeting climate goals. So the figure on this slide shows that although trucking constitutes about 43% of freight ton miles in the US, it is responsible for about 74% of the total emissions associated with moving freight in this country. Decarbonization is challenging in the setting because of the need for high density energy sources for transporting heavy, bulky loads over long distances. Most potential decarbonization pathways will require the build out of new types of refueling infrastructure to provide those alternative energy sources. Yet we already struggle to provide trucking infrastructure in the US, as exemplified by our second motivation, the shortage of truck parking. For years, a majority of truck drivers have reported difficulty finding parking, and expanding access to adequate truck parking has been the subject of extensive work by the US DOT and state agencies over the years. Right now, parking is provided by a mix of public and private providers, which generates a rich set of policy trade-offs. And today, under-providing trucking infrastructure translates into safety concerns, capacity constraints, suboptimal routes, delays. In the future, insufficient infrastructure provision may undermine our efforts to meet climate goals in this sector. So that leads to the specific research questions for this project. So the first question is, how do drivers value route efficiency versus access to complementary infrastructure along the route? So this is, in a sense, the demand side of our model. Then the second question is, what are the incentives for providing trucking infrastructure? And what are the market and non-market barriers that impede optimal infrastructure provision? So this is the supply side of the model. Now, in estimating our model, we're focused on infrastructure in the form of truck stops and truck parking, since that's where we have interesting data today. But we'll be using this model to simulate potential future scenarios around alternative fueling infrastructure. And then the third research question is, how can policymakers address these barriers to support efficient trucking infrastructure, particularly for alternative fuel trucks? So what can economics tell us about why trucking infrastructure might be underprovided? So we're thinking about three categories of frictions here, each of which would warrant potentially different policy responses. So the first is what we call strategic complementarities. And so the idea here is that trucking and trucking infrastructure are complements, which means it's more valuable to provide one when the other is widely available. Likewise, trucking operates on a spatial network, so providing infrastructure along a given route is more valuable when there is infrastructure available at other points on that route. But because infrastructure providers may not directly profit from all of the spillovers that they create in the spatial network or for trucking companies, they may underprovide such infrastructure relative to the optimal level. Then the second potential friction is market power among infrastructure providers. And so while truck stops along a route are complements to truck stops further away on the same route, when those stops are located too close to each other, they may act more like substitutes. And in that case, infrastructure providers with large market shares may choose not to construct new truck stops because they don't want to take business away from nearby truck stops that they already own. And then the final set of potential barriers are regulatory, especially zoning. And so existing regulations may restrict the set of available locations where trucking infrastructure may be built, thereby raising the cost of building new infrastructure or even preventing infrastructure from being built at all. And so existing reports from industry groups and federal agencies have referred to all three of these different economic forces as potential explanations for the underprovision of truck stops and truck parking. And each of these potential barriers would also likely affect the build out of alternative fueling infrastructure. And so we want to build an empirical model to disentangle these potential mechanisms and then simulate how they might respond to alternative policies. So to answer these questions, we are relying on many different data sources on the truck freight market. So the first four bullets on this slide refer to data sets that have already been collected and are already in use. And then the final two bullets refer to data sets that we are acquiring and incorporating into the model with the help of this grant. So most notably, the grant support is enabling us to transition from using aggregate freight traffic data to instead high-frequency GPS pings of truck locations, as well as to transition from relying on a snapshot of trucking infrastructure at one moment in time to instead looking at entry and exit of truck stops over time. And I will talk more in the subsequent slides about exactly how these two additional data sources will allow us to answer more interesting questions. But let me first share some results using the first 4 data sets from the list that I just shared. So in initial work for this research agenda, my collaborators explored what we can learn about driver trade-offs using aggregate traffic data. And so this analysis constructed measures of per mile density of public truck parking spaces using the Jason's Law data set, and then compared that to the truck data the traffic data in the HPMS. And so the two have a modest correlation of 0.38. This analysis then used the cross-sectional relationships between infrastructure density and traffic to estimate how drivers respond to changes in infrastructure in the routes that they choose. So how do drivers alter their routes in response to the availability of truck stops and truck parking? So as an illustration of the findings, consider this example. So for this area of the Midwest, we can suppose that we add an additional parking space along the yellow segment of the highway. So simulations based on the model estimates imply that this additional infrastructure would lead to decreases in traffic along the substitute routes, which are the ones colored in red, and then increases in traffic along the complementary routes, which are the ones colored in blue. And so as you can see here, the implications of public policies supporting additional truck parking in one location are potentially quite nuanced because of this substitutability and complements. So now let me talk about how we are building on these initial results. So as I've just described, understanding how drivers respond to the availability of truck stops and truck parking helps us to understand the benefits of introducing additional trucking infrastructure. But what about the costs of this infrastructure? So by understanding the patterns of truck stop entry and exit over time, we can use our model to obtain more reliable estimates of the shadow cost of new trucking infrastructure. So this would include, for example, the shadow costs imposed by restrictive zoning. So to do this part of the analysis, we are digitizing multiple years of the Trucker's Friend publication. So illustrated on this slide, this was an annual periodical that provides a registry of trucking facilities and parking spaces across the US, as well as other important characteristics such as the network of fuel cards. And so you can see here just how rich the set of characteristics provided in this data is. So single snapshots of the Trucker's Friend data have been previously used by the DOT to measure access to parking. And so our contribution is helping to develop a panel which tracks entry and exit over time. So once each issue is digitized, we then geocode the entries to arrive at the following. So we have here annual maps of truck stops and truck parking facilities. And so in the figures on this slide, each circle represents a truck stop. The filled in circles represent truck stops with parking. And then the size of the circle represents the number of parking spots. So by comparing across years, such as the 2 years we see on this slide, we can infer patterns of entry and exit. And then we'll then associate these patterns of entry and exit with spatial variation in our potential causes. So the strategic complementarities, market power, and non-market barriers to entry. Then the second data set that we are incorporating into the analysis is high frequency data on trips taken by actual trucks from INRIX. And so this data set tells us about the structure of routes in a way that we can't get just from the aggregate traffic data, especially outside the for-hire market. So in particular, do the routes look like the left side, where we have out and back trips with potentially more room for home-based refueling, or do routes look like the right side, decentralized with more room for public or third-party refueling? So this data set will help us refine the existing model of driver behavior so that it can more effectively answer questions relevant for zero emissions trucking. So how are we applying this model to trucking decarbonization? So we're focusing on the regional freight market because we think that the questions about infrastructure provision are especially rich in this setting. So at one end of the distribution of trip length, the shortest trips can rely on refueling or recharging at base, which creates greater confidence that electric trucks will be feasible in this submarket and that shippers will more readily internalize the benefits of installing charging infrastructure. Then at the other end of the distribution, the longest trips will require recharging or refueling away from home base. And there's considerable uncertainty about whether electricity, hydrogen drive fuels, renewable diesel, or some other energy source will be most effective in this submarket. And then the regional market lies in the middle. So fleets may rely primarily on recharging at home base, but still use external infrastructure to extend the driving range of their vehicles, for example. So how might support for within fleet charging stations, private en route charging stations, or public access en route charging stations interact with the barriers to infrastructure provision that we discussed earlier? And what does that mean for the feasibility of electric trucks in the regional market, given various assumptions about key technological parameters? So to briefly conclude, trucking infrastructure availability affects transportation efficiency today, and then the viability of future decarbonization pathways. The preliminary results using the aggregate traffic data provide insight into driver trade-offs between route efficiency and infrastructure availability. And then our ongoing work will inform estimates of the infrastructure costs and simulations of charging infrastructure in regional freight markets. So looking forward to comments and questions either now or in follow-up, and our emails are included on this slide, and Ron is on the Zoom as well. So thank you.